Okay, let's start. So we discussed about this Nestor momentum last time, and yeah. So as an advanced methods, there is a ADA grad which is not actually used, and yeah, based on a similar motivation. I mean, yeah, we have this RMS prop, and what's the motivation here? So in this figure, I mean, this is the bad condition number case, right? Right. So in this case, the slope is usually really high along the one particular direction, and the slope in the other directions may not be that high, right? So that way, if we just collect the gradient values from each dimensions, and then those values might be much different across different dimensions, right? So starting from maybe 1, 3 as our two of our parameters, and then the first gradient might be 100 and maybe 2, and then we will do the updating like this, and then given the new point, we evaluate our gradient once again, and then maybe this grade step size times 150 and -1, and in the next step minus 200 and maybe 1.5, for example. So in this case, if we collect those values, 100, 150 and -200, those values will have large absolute values, and then the second dimension will have much smaller values, right? So we mitigate this kind of effect in the RMS prop. So that's So in the RMS prop, for this value, instead of using this value, we basically divide it by the square root of 100 squared and 150 squared and minus 200 squared, and then divided divided by 3. Although it is not the exact formula because we are using a running average that assigns a different weight on different time steps sample, right? But yeah, this is rough idea. So that if the previous movements or gradient magnitude were really large, and then we just scale it down properly, but at the same time for these guys, it will not be scaled that much, right? So that way, we want to kind of make approximately the same amount of the gradient or same gradient magnitude across different dimensions. So that's the idea of this RMS prop. Okay, so that way we accumulate this gradient squared, and then compute the running average, and then divide it, dimension-wise, right? Okay, Adam is the combination of this RMS prop and momentum, right? So instead of just using the gradient itself, so we basically compute this momentum, which works as the gradient vector when updating this x, right? So overall, this is the probably one of the most frequently used optimizer in many practical deep learning architectures. Okay, and then we discussed about this tricky kind of issue about this bias correction stuff. Okay, then one thing that I wanted to show last time was this guy, CS231 lecture note. And so here, so this is a saddle point example. So given this saddle point, the gradient across all the different dimensions will almost be 0, right? But if we have the momentum factor, and then even though the gradient magnitude is really small at a particular time step, if it was accumulated with the same signs, and then at a current time step, it will have some non-trivial amount of gradients. So it's easy to escape from this saddle point. Okay. Then also in this case, it's a much complex landscape of our function. So here, intuitively, the color gets more blue, and then it's a lower kind of function value, right? So we want to, arrive this kind of valley, which is the lowest height. Okay, so in this case, we can see different behaviors of different algorithms, and we see a stochastic gradient descent as red, and the momentum and the Nesterov momentum, and ADA grad and the RMS prop, and also we haven't studied this ADA delta, but we will just skip this in our lecture. But anyways, we can see some interesting aspects. Like in the case of a momentum, it will overshoot a lot, right? So around this region, even though it is an uphill because of the accumulated gradient, it will still go up, right? But eventually it will go down to the this local minima. Okay, and overall among these, RMS prob and ADA delta seem to work well, right? But if you use an ADAM here, and then it will work as good as those algorithms, or sometimes it's even better. Okay, in terms of the convergence speed, okay, and also it's giving a better quality of a local minima, which means at the converging point, we may have a much smaller loss values when using ADAM compared to other methods. Okay, and one of the questions posted in the slido.com was about this first order and the second order optimization. So it is related to this Taylor expansion. Okay, so in this Taylor expansion is to approximate this complicated functions as a simple first order or the second order degree polynomials. Like given this complex functions, we can approximate it as ax plus b, or as a second order polynomials, and then we can just approximate it in these two forms, right? So in order to approximate this given complex function as this simpler functions, we have to first fix a particular point, right? So that's usually how this Taylor expansion or Taylor approximation works. So for example, so we specify a particular point, and then how we approximate this complicated function into this form is by making the the zeroth order and the first order derivative the same between the two graphs. Okay, so in this case, so suppose we just approximated this complex graph as single line. Okay, in that case, it means suppose this function is f and this approximated function as g. So our g is this kind of function. Okay, so these are approximated function. Okay, and then we first make this a single point equal between these two graphs, and this is a zeroth order equation. And the first order equation is f prime x equals g prime x, which makes the first derivative, first order derivative to be the same between the two graphs. Especially at this particular point x. So again, we start with the particular point x comma y, right? And then So we find out this A and B by just setting this guy and these two equations. By satisfying these two equations, we find out this A and B. So this is the first order approximation, and this is basically done by this Taylor expansion. Okay, but we can, in the case of this Taylor expansion, it is related to gradient descent because at this particular point, if we approximate this whole function as this a simple line, the way, the direction that we have to go in order to get lower in terms of a function value will be like this direction, right? So that is the intuition used in the gradient descent. But in the case of second order optimization, we basically approximate this as the second order polynomial, and we basically add another constraint or another equation like this. Okay, and so in this case, the function value itself should match, and the first order derivative, which means the slope, should match, and also the degree of this increase or the acceleration or this second order derivative should also match, right? So in that case, at this particular point, we can suppose that approximated graph is represented as this blue line. Okay, in this case, because we assume that the entire graph is just like that, and so in the case of this this second order curve, and then we can directly compute the minimum possible point. The minimum point in terms of the function value. Okay, so if we just approximated this graph as 2x squared plus 3x and minus 5, and then the minimum point will be easily computed as negative 3 over 4, right? And so, even though we started from a single particular point, once we approximate it as a second order derivative, a second order polynomial, and then we can just go directly to the minimum possible point based on this second order polynomial assumption. Okay, and then this will be the next point in our iterative optimization. And then at this point, we evaluate our function value. Okay, so we basically moved from here to here, and then our function is over here, and then our second order approximation will be something like this, right? To match the function value itself and first and the second order derivative, and then the minimum point will be somewhere around here, right? So we jump to that point directly. So in terms of the difference between this first order and the second order optimization, the first order optimization is a gradient descent, and the second order works in this manner. And the main difference is that we don't need any step size in the second order optimization, right? Because we can just directly go to the minimum possible point from this second order approximation. But to obtain this second order polynomial as our approximation, it actually involves the second order derivative of our given function. So at this point, what we did was to have the function value itself, and then we computed the gradient, which is the first order derivative with respect to individual variable that we have, right? So if our parameter, the number of parameters are 10, and then what is the first order derivative or the gradient vector dimension? It will be 10-dimensional vector, right? And then we can, how about the second order derivative? So our function itself is a scalar, and we can consider is x1 through x10, right? Okay, and then yeah, that's how we obtain 10 different gradients with respect to individual variable. But in the case of second order derivative, we can actually, yeah, so this could be one possible second order derivative, and maybe 2 and 3 and so on. So that way we may think of like 10 different second order derivative, but actually, in fact, we can think of many other second order derivatives. Like, yeah, we first take the derivative with respect to x1, and then given this function, we also compute its partial derivative with respect to x2. So those two values, yeah, can vary, yeah, from 1 to 10, and so the second order derivative is resulting in, so it's a 10-dimensional vector, and the second order derivative, which is called the Hessian matrix, is having the size of 10 by 10 matrix. Okay, and somehow, yeah, we actually need to compute its inverse matrix. Okay, so computing the inverse matrix, yeah, requires the computational complexity of 10 to the power of, yeah, 10 cubed. Okay, so that way it's involving a lot of computation, and also, yeah, even if we follow this second order derivative, we basically have to maintain this much, this much size of the matrix, right? So it's quadratic in terms of the number of parameters, and as you saw in the VGGNet or ResNet and so on, the total number of parameters can be, yeah, more than 1 million. So, yeah, we can somehow manage the million number of parameters within our GPU or our computers, but the square root of these numbers, yeah, cannot be manageable. Okay, so that way in practice, this second order optimization is not used much. Okay, any questions about this? 네. 지난번보다 잘 안 들려요? 마이크를 여기 올려놓으면 뭐가 이게 펜을 쓰는 소리까지 가고 내가 그런데 지금 잘 들려? 네. Any other questions other than increasing voice? Okay, and yeah, there are many different second order optimization methods, and this BFGS or LBFGS, which reduces the required size, memory size. Yeah, this LBFGS is the most popular one. Yeah, but yeah, when training the neural net, because the number of parameters is too large, so yeah, we don't use this second order optimization much. Okay, and the model ensembles and the regularizations. So have you guys understand this, right? So it's like, so starting from here, yeah, suppose we arrived at this point, which is like a little bit flat region, but the gradient is not completely zero, right? So in this case, yeah, the gradient became close to zero, and thus we don't have a momentum. Yeah, we don't actually have the enough force to escape out of that point, right? And so if our loss function plateaus, and then, yeah, sometimes we actually decrease the learning rate to actually go to really fine point. Okay, really so it's like, so if we have this loss function, and then starting from here, and then suppose we arrived at this point, and then we have some gradient, and then if we use still the learning rate that we used in the previous iterations, and then it might be too high to reach at this exact local minima or our global optimal point, right? So in this case, it may be like bouncing around, okay, because our learning rate is too high to reach at this exact point. So in that case, we sometimes reduce the learning rate, okay. So that is one strategy. But what if the current point is like a saddle point where we still have some direction to go down, but at the current position, it is almost flat. So in that case, we can actually, boost up our learning rate as a bigger ones, and then that can help to escape from a saddle point. Okay, so this is one kind of a strategy to adaptively change our learning rate. And let me show another strategy. So I'm not sure if we can cover this transformer model, but at least we will cover the notion of the self-attention, which is really exciting and interesting kind of technique, which brought a lot of performance improvements in many different applications. And so this transformer is widely used, especially in the natural language domain. Okay. So in this transformer, it actually has used a different learning rate, adaptive changes of learning rate. So what they used is like this. So we start from really small learning rate. So this is the learning rate graph, and then x value is the iteration index. So as we go on, we gradually increase the learning rate. So that means, why do we use a small learning rate at first or at the initial stage? Because we start from really at the random point, right? And at the random point, our gradient might, the magnitude of our gradient might be sufficiently large, right? So at that moment, if we use the high learning rate, and then it can diverge, right? So for example, in this simple case, suppose we started from here, and the gradient is large, and the learning rate is large, and then it can move this guy to over here, and then the gradient became even larger, right? And if we use the same step size, and then it will just jump it to another point. So it's actually making this our point diverge out of this global or our optimal point. So that way we basically use a small learning rate at first, and then if the gradient gets smaller and smaller, and then in order to give a more kind of momentum, more force, we use a higher learning rate. Okay, and then now we start to decay or decrease the learning rate, because it is assuming that we arrived at this region where the global optimum can be found by really fine-tuning that point, right? So that way we reduce the learning rate. Okay, so this is called the warm-up scheduler of our learning rate. So this is another kind of trick that this method has used. Okay, I believe you guys have understood the main idea of the dropout. The main idea of dropout is that we don't want to rely on only some small portion of the information, right? So if we want to recognize a cat, and then we want to kind of aggregate all the information that are given to us, instead of just relying on a single particular information. So suppose our training data, in our training data, cat image all has the ear, for example, and then this cat will have a lot of other characteristics or other features that will distinguish cat from other objects, right? But still, if our training image has all the ears for this cat images, and then it has no problems to rely only on this information of whether we have a ear or not, right? So in that case, what if our test data gives a cat image that doesn't have an ear due to like a cropped image, and then yeah, it will have no way to recognize it as cat, right? So that way we intentionally and randomly drop out this information, right? So that is the main idea of this dropout. So that will generally help to improve the performance of unseen data, right? So that way it can be viewed as a regularization method. Okay, and also it can be viewed as the ensembling many different models within a single training or single model. And have you understood this part? How we adjust the test, our neural net output in the testing phase? So suppose this output takes the 3 input node, maybe X, Y, Z, and during the training time, they are randomly dropped out with the 30% of the probability. So overall, this node will be present with the 70% of probability, and the other 30% probability, it will be dropped out, right? And so yeah, they will be added anyways with some weight values assigned to each of them. And then if they are dropped out with the ratio of the 70% probability, and then the usual magnitude or usual amount that is collected at this node, yeah, will be just 70% of the magnitude computed from all the nodes, right? So in the case of training time, yeah, we randomly drop or remove them with some probability, but during the test time, yeah, we use the full capability of our trained network. So we don't actually drop out any node during the test time, right? So in that case, this will have an unintentional effect that the magnitude that is received by this node is increased, right? What is the ratio of this increase? Because we dropped out with the 30% probability, or yeah, we made them alive with the 70% of the probability, and when using all of them, and then we will have like 0.7, like 1 over 0.7, yeah, ratio. I mean, that is the ratio of this increase of the received output, right? So that will mess up our batch normalization or the ideal range that is given to, ideal range of the input that is given to our nonlinear units and so on, right? So yeah, maintaining the same range of the input or activation values, it is really important. So in order to like adjust this aspect, we actually scale this down by 0.7, right? Okay, so so that is reflected in this code, right? So we don't actually do the dropout during the test phase, but yeah, so we actually scale down, yeah, this output, just like the case where we drop the node with the 30% probability. Okay, so this is one additional code that we have to add in the testing time when using the dropout. And also, you guys understand this inverted dropout, right? So in the case of an inverted dropout, the main idea is that, yeah, so this additional multiplication with the p will actually make our testing time, computing time during the test phase slower, right? Because it is introducing additional computation, right? So we want to make the testing time as fast as just the case without any dropout, right? So we don't, we actually want to remove this guy, right? And then how can we do that? So we maintain the exact same test code like that, which ignores this effect of the dropout, but we actually adjust during the training time. And how? So if we did so in this case, we apply suppose we apply the dropout with the 70% probability of making them alive, and then given this output during our training time, we actually increase it by 1/0.7. Okay, so we basically increase the magnitude of our activation, as the level where we obtain when using the full node without any dropout, right? So okay, so that is this guy, right? So we basically increase the number of, increase each of this activation values, right, while doing the dropout during the training stage. Any questions so far? 네. 네. 그렇죠. 네, 그런데 베리언스가 작아지죠. 근데 이제 배치놈은 그 작아진 베리언스를 기준으로 얘를 노멀라이즈를 하겠죠. 그렇죠? 네. 그러니까 어쨌건 우리의 배치놈, 뒤에서 후처리로 쓰이는 배치놈이든 앞쪽에서 쓰이는 우리의 웨이트든 어찌됐건 얘는 얘대로 이 드롭아웃, 그러니까 10개 중에 3개가 버려지는 상황에서 어떤 최적의 레인지가 되도록 뭔가 이 웨이트가 알아서 키워지거나 아니면 배치놈이 알아서 그걸 뭔가 키워주거나 할 건데, 네. 근데 중요한 거는 트레이닝 할 때는 어쨌건 이게 엔드 투 엔드로 뭔가 되기 때문에 이거는 그냥 알아서 다 되는 거고, 우린 드롭아웃을 적용을 해주기만 하면 되는데, 이제 테스트 타임에서는 드롭아웃을 결론적으로 안 쓰니까. 왜 안 쓰냐? 우리는 뭔가 정보를 빼먹고서는, 그러니까 뭔가 정보를 빼뜨려갖고 학습 때 뭔가 더 하드하게 트레이닝 할 수는 있지만, 이제 테스트에서는 우리의 풀 퍼포먼스를 내야 되기 때문에, 뭐 노드를 이제 뭐 있는 정보를 막 이렇게 막 버리는 게, 없애는 게 이거는 우리가 원하지 않는 거야. 그래서 이제 모든 노드를 다 썼을 때는 거꾸로 이제 그 베리언스가 커지기 때문에 그만큼을 이제 줄여줘. Any other questions? Okay, so that is the dropout, and so batch norm and dropout can both be viewed as the regularization techniques. And some student asked the question about whether we use both of them, or sometimes do we use one of them or not at all. So usually we use the batch norm first, and usually batch norm will work as a sufficient regularizer. So in practice, we don't actually use batch norm and dropout, both or simultaneously. Okay, but between the two, I think to my understanding or to my knowledge, the batch norm is the first that we add as our regularizer. Okay. And also, we can do a lot of data augmentation, and actually this step will work really as an important step to improve your performance. Okay, so in practice, we always don't have an enough number of the data. So we don't just handle the problem where the enough data is provided. Our problem is a quite new problem, and so we want to solve the new problem based on our own collected data, and in many cases the number of data is really small, and so in that case this data augmentation will work as really effective method to improve the performance of an unseen data. So any questions about, so you guys understand this? So this is another kind of randomization, right? So it's like, instead of just the max pooling over this regular grid like this, sometimes we increase or decrease some specific positions window when doing the max pruning. Okay, so that will also give us some randomization during our training time, and which will work also as a regularizer. But yeah, I'm not sure if it is a widely used, but I think it's an interesting idea. Okay, we will actually have an opportunity in the later classes to discuss about this transfer learning, which is a really important concept. And I think, yeah, that's it for chapter 7. Any questions about this chapter 7? Okay, then yeah, regarding chapter 9 about deep learning software, yeah, I actually don't have much background myself. Yeah, because I haven't done any deep learning programming or coding myself. Yeah, all my research about this deep learning is programmed or implemented by my students or other collaborators. So I just do the writing and giving some idea or directions. But anyway, so yeah, I actually don't have much background or insights to teach. I mean, enough background to teach about these, but yeah, but at a high level or in principle, among the many softwares, you guys have to understand carefully about the difference between static and dynamic graph. Okay. There was a slide, right? So, yeah, one convenient thing when using this deep learning library is that, yeah, most of them will provide the backpropagation function. So once we define our forward propagation, and then the formula for our backpropagation is automatically given or automatically computed by our deep learning software. So that way, even though we studied a lot on the backpropagation, which is really important still, but when actually programming or when doing your homework, for example, you don't actually need to write your own backpropagation code because that is done by this deep learning libraries. But still, I think how this backpropagation works in detail is really, really important because sometimes there are some layers that is not differentiable, for example. Yeah, so in that case, so for example, let me give a simple example. Yeah, instead of the sigmoid, the sigmoid function is looking like this, right? So it is differentiable. But what if we use this guy? So this will work just similarly as a sigmoid nonlinear activation. So if it is a zero, I mean negative output, and then it will output zero, I mean negative input, and then it will output as 0, and if it is a positive input, and then it will give us output as 1, right? So this is a discrete version of the sigmoid, right? So we have no problem of using this discrete version of the activation function, right? But the problem of it is that this guy is not differentiable. But I'm not sure if it's a correct way to describe the situation, because I mean, it is differentiable except for this point, right? So the only point that is not differentiable is at 0, right? Because, I mean, what is the necessary condition to be differentiable? It is at least the condition that the function should be continuous. So if the function is not continuous at that particular point, and then we cannot obtain the derivative, right? But what about the other points except for this 0, right? So suppose we are given the input as 3, and then what is the gradient at this point? The gradient is 0 exactly, right? So it is differentiable, but it actually prevents our networks from being trained, right? Because when doing the backpropagation on this layer, and then whatever gradient of dy comes in from the upstream, our gradient to be multiplied with that upstream gradient will be always 0, right? So that kind of flat shape of our graph is always giving the 0 gradient. So that will give us the problem of not being able to train our network of the lower layer. Okay. But there are some fancy tricks to actually compute the gradients. Okay, so there are many interesting or advanced techniques that can also incorporate this discrete functions and also still being able to perform the backpropagation. Okay. Okay, so back to this static versus dynamic graph. So I think I encourage you to carefully review the CS231 and lectures, but the main idea is that at every iteration we basically create the connection from scratch. Okay, so we can we basically define or assign or allocate the memory for our nodes, right? So one node and the other node, right? And then that is just assigning the memory allocation for our variable, whether it's a parameter or activation value or input or output activations. And then there are connections like, okay, after performing this function and then that output should be given as an input to another function and so on. This whole path of this computations is actually set up or created from scratch at every iteration of our gradient descent update. So that is the idea of this dynamic graph, right? So it seemed to be really like it seemed to be a little inefficient, right? So in that sense, once we just set up this connections or how this computational graph is connected exactly in advance, and then there exists some efficiency that we can kind of incorporate, but that also has some disadvantages, right? So what if our data, what if our data changes and then our computational graph should also change, right? So for example, there was an example of like a if statement, right? So in that case, it is not a static graph. So depending on our input data, we have to really route differently this input to different node, right? So that is kind of notion of the output, the dynamic graph. And this dynamic graph is also becoming really critical in the recurrent neural network or long short-term memory or gated recurrent units that we will study right after the midterm exam. Okay, so in that case, like the coding or programming this RNNs using this static graph-based deep learning library such as TensorFlow is really becoming messy. Okay, so the code is really becoming large and getting kind of spaghetti kind of shaped code. And so in that case, the dynamic graph-based deep learning libraries is really useful for dealing with this RNNs and so on. But I will skip the details because I don't have much ideas or much more knowledge than this original lecture. Any questions so far? Okay, then let's finish this chapter 8 and then move on to chapter 9. And the first thing that we will study is the VGGNet of this. So some student also asked the question about it. So the receptive field, let me just describe what the receptive field, and I brought some paper. So this is a kind of video prediction paper. So the task itself is not really relevant from our context, but I wanted to bring this figure. Okay, so let's just ignore about this frame t-1 and t, and let's assume that is our layer 1 and layer 2. And this is a kind of example of a convolution, right? So in order to produce one single output, so how many pixels do we look at? So center that here, and we are looking at like plus and minus 1 pixel kind of neighboring kind of pixels, right? So in this case, we call this situation as like the receptor field being 3 by 3, right? But what if we just stack another layers, right? Like this, okay? So so let's consider this 3 by 3 and 3 by 3 convolution, okay? So in this case, yeah, let's just use this guy. So what is the receptive field from, yeah, let's suppose this is an input image, okay? This is our input image. And then what is the receptive field, or the size of the regions that is involved to compute this single activation map in the first and the second hidden layer, okay? So this one, we'll look at this 3 by 3 in the previous layer input, previous layer output, right? And then now, what about this guy? This guy is, which regions does it look at in this input? So this guy is looking at this region, and this guy is looking at this region, and so on, right? So when considering this 3 by 3 convolution, this is a single node. Single node is looking at 3 by 3 region, and also it is further increased in terms of the receptive field in the case of this input activation map or input image. What is the receptive field size? It is 5 by 5, okay? And then let's think of some other cases. How about like 5 by 5, two stacked convolution layers of using 5 by 5 filters. So in this case, 5 by 5. And what about here? Is it like 25 by 25? Would it be correct? Okay. So yeah, because there are not many pixels or dots over here, let's just increase the filter size as a 4 by 4. Okay, and then you will have this activation map. And then this guy will also look at the other regions, right? In the input image, and this guy will have this regions, and so on. So it is not really like multiplication, right? It is really addition, right? So given the single pixel, because we can think of this mapping from, as I mentioned, we can think of this mapping as from this point into this point, and then if our window size was 1 by 1, and then our receptive field will just stay as the same, right, as 1 by 1. But if we use the 3 by 3 filters, and then it will give one more kind of pixels on the left, right, and up and down, right? And then this guy, when considering the single pixel mapping over here, and then how many additional pixels can we look at in the input layer? So if we use the 3 by 3, and then it will still give another one more pixels on the left, right? So one pixel left and another pixel left, right? So it is really linear, right? With linear kind of increase, right? So in the case of 5 by 5, so it is increasing like two more pixels on the left, and then also 2 more pixels on the left in another layer, right? So in the case of 5 by 5 layers, what will be the input activation map? So 5 by 5, and then, so we know that, right? So this one is the receptive field corresponding to that activation map in the middle. And then it will give us 2 more pixels on the left, right, and up and down, right? And so the receptive field will be 7 by 7, right? So starting from the single pixel, if our convolution is like 2 pixels on the left, like in the case of 3 by 3 pixels, center position is giving us a single additional pixels, and if we pass 2 layers and 2 additional pixels and so on, right? Okay, so you guys now understand clearly about this the meaning of or the notion of this receptive field, right? Okay, and then now let's get back to here. So here the situation is we stacked 3 convolution layers where each convolution layer has the filter size is 3 by 3, right? And so what will be the receptive field size? So starting with the 1 pixel, right? And then left and right, it will give us 2 more pixels in the first convolution and another 2 more pixels in the next convolution. So we are going backward, right? And then 2 more pixels, right, in the very first layer. And thus the receptive field is 7 by 7. So does it make sense? Okay, so so here in the case of an input image, when stacking 3 layers of 3 by 3 convolution layer, and then at the end, each pixel is looking at or involving 7 by 7 kind of large sized window, right, in the input activation. Okay, so in that case, let's just consider another case where we only just have a single convolution layer. Okay, so instead of stacking 3 convolution layers, let's just use a single convolution layer that has the same receptive field. So in that case, we will just use 7 by 7 window or filter as our convolution in our convolution layer when using the single convolution layer to match the receptive field. Okay, so we want to be able to match the receptive field size. Okay, so that's the initial assumption. Okay. Okay, and then now in this particular case, we are considering this situation where we have width and height, and some channel number C. I mean the number of channels in an input activation map is C. Okay, and then let's suppose we want to have another activation map that still has the same channel size as C. Okay, so in this case, let's just compute the number of parameters when just applying the single layer convolution that has the receptive field size as 7 by 7. Okay, and in this case, how many number of parameters do we need? So one filter will have this width and height, and because input activation map is C, so this is the number of parameters required for one single convolution filter, right? And we have to generate the C different channels, and thus we need C filters, right? This is 7 squared, C squared is the total number of parameters needed to have a single convolution layer that has the 7 by 7 receptive field. Okay, and then now, so this is the first situation, and the second situation is, so we stack 3 layers, right? 3 stack layers, let's stack 3 layers, and the input is like this size, and output has this size, and we have a freedom to change our channels in the intermediate layers, but let's just assume that this guy is C, and the next activation map also has C, and also C and C. Okay. So we consider this situation of stacking 3 layers of having 3 by 3 convolution. Okay. And then in this first layer, how many number of parameters do we need? So 3 by 3 is our filter size, and so this is an input, and this is an output, right? Okay, so overall this is a 3 squared, C squared, and we need 3 different layers, right? And so we need 3 sets of this much number of parameters, right? And so overall, 3 times 3 squared, c squared. So if we compare between these two numbers, so this guy is 27, and this guy is 49. So we can see that the first scenario requires much more number of parameters than the second scenario, right? So here again, the assumption is that we want to maintain the same receptive field size. Okay. Okay. So stacking this more number of layers while using really small filter size, so that will give us the smaller number of parameters required to have relatively large receptive field size. Okay, in terms of an input activation map. And at the same time, if we stack these 3 layers, the nonlinear units such as ReLU is introduced at 3 different places. But on the other hand, in the case of a single layer, we have only one chance of adding nonlinear units, right? So we have 3 different places that we can add or inject some nonlinearity, and thus, in general, it is better, okay, adding this nonlinearity more. Okay. So this is the main kind of idea or kind of intent of kind of design kind of rationale or kind of motivation of VGG nets. Okay. So in the VGG net, we only use the smallest possible filter size of 3 by 3, right, to take into account the nearby or spatial kind of patterns. Okay. So any questions? And then now, there was a question about in the Slido. I saw the question about why this nonlinearity is giving the good or better kind of a capability in our neural net, right? So so did I mention about this blog? Posted by this Chris Ola. So he's a researcher working at a Google Brain. But interestingly, he doesn't have any, as I know, he doesn't have any degrees. I mean, higher educational degree such as master's or PhD. So he just graduated as an undergrad and then just directly joined Google at this Google Brain. Anyways, so in his blog, there are many interesting kind of blog articles that allows you to understand the complicated notions involved in the deep learning much easily. Okay, so here there are many different articles that you can read. I actually strongly encourage you to check each post in this blog, and in one of them is showing this simple example. So suppose this is our data. In the context of a binary classification. So, for example, so let's imagine this x and y axis. So this is our feature space, and this is a weight, and maybe this is a height. Okay, and this line is not a kind of a regression line, but it's actually like when given this feature vector, this one has the positive label, and also this one also positive label, and this one has the negative label, and so on. So in this case, when using the linear classifier, such as logistic regression or support vector machines, there is no way to properly classify them because using any single straight line, so we cannot properly separate them into 2 separate regions, right? Okay, so this is the example. So probably this horizontal line might be the best one that has the smallest misclassification rate, right? Okay, so in the case of a linear and the nonlinear unit. I mean, when using a neural net that has this nonlinear transformation in the middle. So that is actually transforming some regions, like, yeah, they are squashing some regions into this form, right? So let's show, let's see the animation. So it seems to be quite slow. Yep. So yeah, it is getting squashed at a certain region, right? So that region is corresponding to the region squashed by our sigmoid function or this nonlinear transformation, right? So yeah, why do we say this word squashing? So in the case of, yeah, I think I described in this manner or not, but yeah, let's just consider the 10H, which is almost the same as this guy, but having a zero mean. So this is a 10H, and then if we don't use the any nonlinear units, and then yeah, let's just replace that nonlinear unit of this 10hx as just y equals x, okay, and then it will correspond to this this line, right? This is y equals x line. So given this input, the output should be here in case of no kind of no transformation or no distortion, but this much value is actually squashed into much smaller value, and that amount of a degree of the squashing gets larger and larger as we get farther and farther from the origin, right? So that way, like, that region is squashed much more, right? And so that is the effect that we see, like at the extreme regions at that corner. Okay. So after squashing these regions selectively or with the different degrees, then starting from this, this is almost the same as the sinusoidal one that we saw. So let's look at the starting situation. So this is the binary classification feature kind of vectors, and then we somehow linearly transform them and then squash some part, okay, and then even though it gets smaller and smaller into like a little bit packed region, yeah, it is packed with the smaller regions, but within that smaller region, okay, at that point, okay, suppose we want to build a linear classifier that perfectly separates them, okay, so we can do the job at that part. So if we was squash it like this, and then we can still form this nicely or linearly separable line, and that given that kind of a warped or squashed feature space, right? So that is the effect of the nonlinearity. Okay. Okay, so in general, nonlinearity will squash or distort some necessary part selectively, okay, so that we can provide better separable feature representation to the next layer, okay. So that is also represented or also shown in this example. So this is like a multi-class classification case. So have you studied about principal component analysis or multi-dimensional scaling, or even T distributed stochastic neighbor embedding? Okay, and then there is a machine learning technique called a dimension reduction. Okay, so dimension reduction is that suppose we have 100 data items where each data item is represented as like 4-dimensional feature vector, like weight, height, and blood type, and his location of a residence, and so on. And then, so we have 100 different vectors in the 4-dimensional space, and then dimension reduction will actually reduce the dimensionality of each 4-dimensional vector into, for example, 2-dimensional vector. Okay, and then how do we do this dimension reduction, and what is the objective in this process? Typically the objective is to preserve their pairwise distance. So for example, okay, in terms of the feature representation, in terms of weight and height and blood type, for example, and if the two persons were having the similar feature representation, having similar weight and similar height and the same blood type, for example, and then their corresponding dimension reduced vector in 2-dimensional space, their distance should also be small. So they should be placed within the similar region. So that is the main idea of this dimension reduction. And one of the widely used dimension reduction algorithm is called, I personally like the name, and also I also do much research on this topic itself. Okay, why it is showing up, but let me just continue this explanation. So this is the example of dimension reduction result of the MNIST data. So you guys know the MNIST data. So MNIST data is 28 by 28 kind of grayscale picture representing a particular digits. And then once we represent it as a single vector, and then the total input dimension is 784, which is a 28 by 28 times 28. And then we suppose we have 100 different digit examples or digit images, and then we apply the dimension reduction to maximally preserve their pairwise distances if they were close in the 784 dimensional space, and then we place them closely in the 2-dimensional space if they are really far apart in the 784 dimensional space, and then we also put them far apart in the 2-dimensional space. And then we basically, once we determine their 2-dimensional positions like this, so if it was 3 by 1, and then we can actually put their points, we can visualize them in this 2D, something called 2D scatter plot. So this is a dimension reduction result in 2-dimensional space of some particular digit image. And then that digit image may have a different digit labels ranging from 0 to 9, right? And then this color indicates that digit label, right? So I wanted to show the MNIST digit example, TSNE visualization example, but Korea Univ AP doesn't allow me to do so. But anyways, so you get the idea, right? So the main idea, or the main point that I want to make over here is that by using the 784 input dimensional representation, then roughly we have maybe several hundred or several thousands of data points, and their colors are represented in terms of their digit label. And thus, roughly, suppose this guy is 0, and then 0 is roughly placed over here, and then many other classes are placed somewhere around in this 2D square. But we can see many overlaps between different digits, right? But once we do the once we go one layer further in our neural nets, and then this neural net, if our so in the case of MNIST digit example, input node will be composed of this 784 nodes, and then suppose we added the fully connected layer, and then we have the 100 nodes, right? And then for each input image, and then it will be represented as 784 dimensional vectors, and then once we transform them by using the first layer, and then that will be transformed into 100 dimensional vector, right? And then we collect those 100-dimensional vectors for each of these data items, and then we redraw or reapply the dimension reduction, and this is the result. And so here you can see that different classes are better separated, right? Because in this input 784 dimensional space, and then it will be really difficult to classify between different classes because they are overlapping significantly. But once we get the one layer further, then those representations will give us more easily separable data representation or feature representation. 네. 그러니까 이 TSN이나 이런 디멘전 리덕션 메소드는 애초에 그 클래스 레이블이 뭔지는 전혀 상관하지 않고 그 해당 데이터 아이템이 뭐 100개가 주어져 있다. 그럼 100개에 대한 페어와이즈 디스턴스가 총 몇 개가 있죠? 100 곱하기 99 나누기 2개가 있잖아요. 언오더드 된 페어에 대해서 모든 페어와이즈 디스턴스를 오리지널 784 디멘전 스페이스에서 계산하면 그만큼 많은 페어와이즈 디스턴스가 있죠. 어쨌건 그 디스턴스를 우리는 입력을 해갖고 이 2D 상에서 얘네들을 잘 흩뿌려서 그들의 2D에서의 그 해당 디스턴스가 저쪽 오리지널 하이 디멘전 스페이스에서 멀었으면 이쪽도 멀게, 저쪽에서 가까웠으면 이쪽 가깝게 하는 거지. 거기서 이제 그 클래스 이 과정 중에는 이 어떤 데이터가 누가 1이었고 누가 이제 뭐 0이었고 누구는 그래서 같은 클래스고 누구는 다른 클래스인지는 전혀 상관하지 않잖아요. 네. 그랬는데 이제 뭔가 해봤더니 이게 대충 보니까 여기서도 보면 인풋에서 이렇게 해봤더니 이제 같은 클래스에 해당하는 데이터 아이템들이 그래도 한 곳에 모이더라. 네. 그러니까 뭔가 우리 데이터가 이제 클래스가 그래도 우리가 처음에 만든 이 784디멘전으로 볼 때 이걸 기준으로 했을 때는 그래도 어느 정도 이렇게 분리가 가능한 형태다라고 우리가 이해해 볼 수가 있고요. 근데 이제 또 우리가 레이블을 설정하는 과정은 피처 벡터랑은 완전히 다르잖아요. 그러니까 똑같은 피처 벡터에 대해서 그러니까 키 몸무게 혈액형에 대해서 우리가 레이블을 뭐 이 사람이 남자냐 여자냐를 줬을 때랑 그 다음에 이 사람이 뭐 연봉이 1억이 넘느냐 아니냐를 했을 때랑 그 레이블만 다르게 줄 수 있잖아요. 같은 피처들에 대해서. 그럼 결국 이 2D 플랫은 변하지 않겠죠. 여기에 어사인되는 컬러만 바뀌겠죠. 그쵸? 왜냐하면 이 2D 디멘전 리덕션은 그 페어와이즈 디스턴스, 그 걔네들이 할당된 추가적인 그 레이블은 전혀 고려를 안 하니까. 네. 그래서 어떨 때는 이제 2D 임베딩을 해놓고 거기에 우리가 추가적으로 우리가 별도의 프로세스를 통해서 별도의 정보를 통해서 레이블을 할당을 했고 그거를 여기 이렇게 컬러를 입혀주면 그게 뭔가 클래스별로 잘 모여진 형태로 나타날 때도 있고 같은 데이터에 대해서 이제 좀 다른 레이블을 할당을 하면 그게 막 서로 섞여 있을 수도 있고 아까 얘기했던 것처럼 같은 클래스인 것 같아 보이는데 이게 여기랑 저기에 이렇게 두 가지 무리로 나타나기도 하고 그거는 이제 우리 데이터가 실제 우리가 부가적으로 주는 이 별도의 이제 레이블링을 할당하는 그 프로세스라고 할까요? 그거랑 그런 식으로 뭔가 미스매치가 있다는 거죠. 답이 되나요? 다른 혹시 질문 있어요? 코리아 이미그레이션 연결이 됐은 걸 알아요. Okay. So intuitively, yeah. So when doing, I once did a group study with some of my earliest students for the Andrew's machine learning class, and there is a homework about this neural net. I mean, implementing this neural net, okay, by using MNIST. So if you did such kind of homework, and then you may have an idea. And then I just an interest, just for fun, I actually applied this TSNE or this dimension reduction algorithm for vector representation extracted from different layers, and then I obtained almost similar result. So we can actually do the if we just design this multi-layer neural nets, and then at each layer we can draw their own 2D scatter plots by using, for example, TSNE, and then you can easily see that the separation becomes more and more, clearer, okay, as we guess later layers. Okay, so so each layer in our neural net is it can be understood or it can be viewed as like given really messy high-dimensional representation or multi-dimensional representation. Each layer is actually gradually processing or gradually transforming your data into another multi-dimensional vectors, but those multi-dimensional vectors are formed in a way that they are like a better separate, better kind of classified or separated by using kind of simple like linear classifier, right? Because at the end, so if we do this multi-layer multi-layer neural net, and at the end, when doing the binary classification or the multi-class classification, at the last layer, it will always be the linear classifier, right? So if we achieve the high performance, and then it means just one layer before, okay, that layer is providing like easily and also linearly separable vector representations of our data, right? So that way, this neural net is like improving the vector representation of the same data gradually over layers, okay, so that it is better separated with respect to our given labels. Okay, so that way, this neural net is also called representation learning. Okay, representation learning. It is learning the representations, for our own purpose. So if our purpose is to classify an image between the male and the female, and then given that label, once the training is done, and then each layer is gradually improving the separability of our data in our feature space, with respect to the given labels. Okay, so that way, it is just called the deep learning is often called the representation learning. And also, if you think of your projects, and then there is one emerging kind of conference called iClear. So have you guys heard about this conference name, ICLR? So there are the three major conferences within the machine learning and deep learning areas, although there are many other neighboring kind of conferences focusing on a particular application, such as computer vision or natural language and speech and so on. But just purely focusing on deep learning itself or machine learning itself, there are three major conferences, which are iClear, and another one is NIPS, and so these are the major ones. And these two have been around for several decades, for at least 10 to 20 years, I think. But this iClear has started just maybe just 5 or 6 ago, or 5 years ago, or 6 or 7 years ago. So it is a really new kind of conference, but that is becoming that became really quickly the most prestigious conference within this domain. But anyways, the reason why I'm introducing this is because this is the acronym for International Conference on Learning Representation. Okay, the learning representations is the key concept or key task in almost all the neural net or deep learning tasks. Okay, so back to this VGG case. We can understand that having more chances or more opportunities to introduce nonlinearity will give us more opportunities to selectively squash some regions so that we can provide a better separability to the next layer. Okay, and also this VGGNet, although there are better alternatives, including Google, such as GoogleNet and ResNet, but due to its simplicity, VGGNet is also quite widely used still in these days. Okay, and you guys understand this, right? So yeah, the number of the size of an activation and the number of parameters. And I think we briefly discussed about it, right, by using some figures, right? So yeah, so in terms of an activation, this gets largest, and in terms of the number of parameters per layers, and this the first fully connected layer will have the largest number of parameters. So yeah, this inception module, although it's a naive one, yeah, this is the inception module, and let's look at the naive one first. So let's just understand it more carefully. So yeah, we can think of this one by one convolution. So at first, when studying this, it didn't make sense to me because convolution is actually extracting out some spatial patterns, right? So the smallest possible filter size could be, it should be 3 by 3, right? Because that way, this is the smallest size involving multiple different pixels, so that we can define a particular pattern, whether it is like this or maybe like this, right? So in order to determine this particular spatial patterns, we don't actually, we cannot do this kind of job using a convolution filter using a single pixel, right? But still, this one by one convolution has the effect. So that effect is as follows. So okay, so let's think of a one by one conv here, and then let's first think of the filter size. So the filter size is 1 by 1, and what is the depth? Depth is 3 in this particular case, right? And then, okay, this guy is placed over here to obtain the inner product output, right? And that way we obtain the single output over here, and then when moving that filters to the next position, and then we obtain another activation output, and that way we still have this 4 by 4 activation map, right? And then what is the characteristic of this value? So this value is actually a linear combination of these 3 different values. Okay, so if it has 3 channels, and each channel will have its own meaning. So for example, this guy is the how strongly a particular pattern exists in that particular position. And so the first channel is looking at the cat's eye, and the second channel is cat's eyebrow, and the third channel is cat's nose, for example. And then if we just combine those 3 informations, and then this single activation map can be representing some information like, okay, so it is activated, or it gets a high activation value when the cat's nose is found significantly, but cat's eyebrow is not found significantly, but also cat's nose is also found significantly. So that way we can kind of combine those informations, distributed or informations across different channels into a single value, right? So if we have another filter of 1 by 1 having 3 channels, and then it will have its own kind of linear combination weight. So for example, linear combination weight was 1, 2, and -1. And then maybe another linear combination weight will be 3 and -2 and 0. So different linear combinations that combines different channel activations at the input level. Okay, so that way we can have a different way of combining those different information. So that is the meaning of the 1 by 1 conv. Okay, so the time's up, and I think it's probably the last class before our midterm exam. Okay, but yeah, the exam scope will be based on the entire chapter 9. Okay, even though I wanted to give more explanations about this chapter, but yeah, we will continue after the exam. But still, the exam scope is up to this chapter 9. Okay. Yeah, and also if you have any questions, and then you can post it in the Slido, and then I'll give an answer with my best at the KakaoTalk room.
배치놈을 레루 다음에 정해도 되나요?
그렇지는 보통 않아요. 네. 그러니까 배치놈은 거의
레루 전에.
네, 항상 그게 이제 어떤 난리니언이든 하여튼 난리니언이 직전에 넣는다고 생각하면 돼요.
파이썬 코드를 보니까 설계를 하잖아요. 근데 레루 다음에 배치가 이렇게 나와요.
아 그래요?
네. 왜 이러지?
그거는 좀 그러니까 뉴럴넷은 사실 이게 안 될 건 없어요. 그러니까 포워드를 우리가 쭉 그러니까 그 합성함수로서 포워드를 구성하고 그게 다 디퍼런셜을 하고 그렇게 해서 그레디언트가 뒤쪽까지 와서 학습만 된다면 뭐든지 안 될 건 없거든요. 근데 이제 다만 그게 말이 되느냐 안 되느냐가 좀 차이인데 근데 이제 내 생각에는 그래서 사실 이걸 내가 단정적으로 그 뒤에는 무조건 넣을 수 없다라고 이야기하는 게 그랬다가 맨날 틀렸던 적들이 좀 종종 있어서 그런데 기본적으로 내가 알고 있는 것은 대부분의 경우는 난이니어 직전에 나와요.
행복하게 핵심 아이디어 한번 거.
핵심 아이디어요?
네.
그러니까 여기에 이제 그러니까 이 채널에 각각의 우리가 어떤 필요한 어떤 정보들이 이렇게 산재되어 있는 거예요.
네.
산재되어 있고 각 위치에서 발견된 서로 다른 그 산재된 정보들을 뭔가 합쳐서 새로운 어떤 액티베이션 맵을 만들어주고 싶은 거예요.
이 세 개의 채널을 하나로 이렇게 만들어서.
네. 왜냐하면 여기에 주어지는 이 세 개의 정보를 세 개의 채널의 그 같은 픽셀 내에서 주어진 그 세 개의 서로 다른 정보를 뭔가 1로 리니어리 컴바인해서 나타내는 요 정보. 요 정보는 예를 들면 아까 얘기했던 것처럼 이게 뭐 강아지, 고양이 눈이 있고 뭐 이게 눈썹이 있는데 예를 들면 뭐 강아지의 뭐 약간 고양이의 코가 없어야만 이 값이 커지고 같이 발견되면 뭔가 이 값은 작아지겠죠. 그런 식으로 저걸 어떤 형태로 우리가 좀 원하는 저것도 다 학습에 의해서 당연히 결정이 되면 뭔가 좀 이거를 한번 섞어주는 거예요. 근데 그 섞어주는 게 이 채널 쪽에서만 섞어주지 이 서로 다른 인접한 픽셀, 이 옆에 있는 픽셀들의 정보들을 가지고 와서 섞는 게 이게 컨브의 기본 아이디어인데 원 바이 원 컨브는 그 픽셀만 보지 그 주변 왼쪽, 오른쪽, 위아래 픽셀 정보의 패턴은 안 보겠다는 거죠.
네, 이해했어요.
아까 마지막에 설명하신 부분에서 시그모이드 한 100개 이거 한 번에 웨이트 학습 끝난 다음에 시킨 거잖아요.
네.
여기서 만약에 하나의 논리니어리티가 한 번에 꾸기는 데 의미가 있는 거라면
네.
왜 한 네트워크에서 렐루 쓰면 렐루만 쓰고 시그모이드는 시그모이드만 쓰고 왜 한 가지만 쓰는 거죠?
그 한 가지만 쓰는 거요? 네. 그러니까 렐루든 그러니까 시그모이드든 꾸기는 건 마찬가지예요. 네, 꾸기는 건 이제 마찬가지인데 이제 그게 첫 번째 레이어에서 렐루, 두 번째 레이어에서 렐루 이거는 각 레이어별로 꾸겨지는 그 영역은 다 다른 거잖아요. 네. 그렇기 때문에 이제 멀티 레이어로 구성된 우리 뉴럴넷에서 각 레이어별로 이렇게 같은 난리니어 유닛을 쓰는 거는 사실 괜찮아요. 그거는 맞죠, 여전히. 여러 번 꾸길 수 있다는 그거는 여전히 성립하고. 근데 이제 뭐 여기선 렐루, 저기선 이제 시그모이드로 쓰지 않는 이유는 그냥 편의성 때문에라고 생각하면 될 것 같고요. 일단은 네, 편의성 때문에라고 생각하면 될 것 같고 이게 뒤쪽에 가면은 또 흥미로운 여러 구조가 나오는데 이게 네트워크를 사실 아웃풋을 뭔가 이렇게 두 개를 만들어 갖고 그러니까 여기서 이것도 지금 이 구글넷 같은 인셉션 모듈도 지금 이게 뭔가 브랜칭을 하잖아요. 이쪽 브랜칭을 해갖고 이거를 결국은 합친 거잖아요.
네.
근데 이 합친 걸 어떻게 합쳤느냐? 여기선 컨캣을 해갖고 합친 거라고. 채널별로 이렇게 쭉 붙인 거예요.
네.
근데 이 합치는 거를, 이 합치는 펑션 자체도 우리가 여러 가지 흥미로운 방식으로 정의를 할 수가 있어요. 예를 들면 여기서 나온 거를 이쪽에 뭔가 엘리먼트 와이즈로 곱셈을 하는 거예요. 그러니까 뭐 예를 들면 여기가 3x3 컴보고 여기가 5x5 컴보다. 근데 이거를 이쪽에 뭔가 곱한다. 그런 식으로 여기서 뭔가 그 두 개의 정보를 합칠 수가 있겠죠.
네네네.
그러면 뭐 그런 식으로 만약에 한다면 이게 합칠 때 여기에 각각에 얘는 뭔가 렐루를 통과시키고 얘는 뭔가 시그모이드를 통과시키고 그렇게 해서 두 개를 곱하면 이게 어떤 효과가 있냐면 렐루는 일단 그냥 렐로 생각하지 말고 여기는 난리니어 유닛이 없다고 생각하고 리니어 아웃풋이고 여기에는 뭔가 얻었는데 얘랑 똑같은 필터 개수랑 사이즈를 해갖고 뭔가 같은 어떤 액티베이션 사이즈를 얻었는데 걔는 시그모이드를 통과했으면 각각의 값들이 뭐냐 하면 0에서 1 사이가 되잖아요. 그러면 이 값을 여기다 곱해요. 한 모든 그 액티베이션 맵이 뭐 30 곱하기 20 곱하기 5다. 그러면 그 똑같은 사이즈 액티베이션인데 얘만 시그모이드를 해갖고 이렇게 포개갖고 값들을 싹 곱하면 그게 이제 뭐가 되냐면 여기서 만든 선형 결합에서 만든 아웃풋의 하나하나의 값에 내가 서로 다른 웨이팅 값을 주는 거예요. 0에서 1 사이. 그러니까 어떤 값은 내가 1을 곱했다면 그걸 그대로 살리고 0을 곱했다면 그걸 이제 죽이는 거예요. 그런 식으로 뭔가 이제 그 어떤 그러면 여기서 시그모이드라는 거는 얘랑 이제 곱해져 갖고 얘를 얼마만큼 내가 죽여줘야 할지 얼마만큼 그 정보를 내가 드러내줘야 할지를 결정해주는 역할로 쓰이는 거잖아요. 그러니까 이제 그때는 그 시그모이드의 특성이 이제 0에서 1 사이 그게 이제 남이랑 곱해지는 그 웨이트로서 쓰여진다. 그런 이제 역할을 우리가 그런 역할을 이제 여기다가 주입을 해갖고 그런 식으로 네트워크를 디자인한 거잖아요. 네, 그런 어떤 특정한 용도일 때 그 어떤 특정한 난리니어 유닛이 쓰여요.
그리고 갑자기 이게 간단한 건 헷갈리는데 시그모이드 안 쓰고 그냥 렐로 써줄 때 딥할 때 왜 그레디언트 베니싱이 일어나요? 그러니까 이 구글 네트에서 초창기 가면은 그레디언트가 잘 전달이 안 돼서 그런 거잖아요. 시그모이드 안 쓰는데 그레디언트가 왜 상처같이 안 가시는 거죠?
이게 기본적으로 이제 이 구글넷도 일단은 기본적으로 레이어가 깊어지면 여기서 이제 그러니까 이제 렐루라는 게 기본적으로 이제 그러니까 누구는 살리고 누구는 완전히 죽이는 형태라 그랬잖아요. 그 죽은 애 뒤쪽에 연결된 거는 그냥 다 죽은 거죠. 그러니까 뭐 물론 이 누구는 죽었고 누구는 살았고 그게 또 백크랍이 되면 어쨌건 그게 또 선형결합으로 또 연결이 되어져 있는 것도 걔가 있기 때문에 또 살은 애들만 얘한테 전달을 뭔가 백크랍을 해주는 거예요. 그래갖고 사실 백크랍이 끝까지 다 갈 수도 있긴 한데 그렇지만 좀 많이 죽을 거 아니에요. 여러 번 통과를 시키면.
네네. 마지막으로 이따가 약간 레프레젠트 러닝이라는 게 뜻을
그러니까 그게 표상을 학습한다 이건데 표상을 학습하는 게 이제 뭐냐면 그게 이제 뭔가 이제 워드 인베딩이라는 주제도 있고 뭐 여러 가지 뭔가 주제들이 있는데 요즘 이제 뭘 하냐면 그 아까도 봤듯이 어떤 주어진 이미지가 있다라고 하면 이미지가 있을 때 그거를 나타내는 우리가 그러니까 가장 첫 번째로 우리가 그걸 나타내는 방식은 어떤 거냐? 그냥 픽셀들을 28x28에 뭔가 픽셀들이 있으면 그걸 한 줄로 핀 거잖아요. 그거가 가지는 그 디멘전의 의미는 어떤 특정한 위치의 픽셀 값인 거잖아요. 그게 어떻게 보면 그 이미지를 벡터로 나타낸 하나의 방법이에요. 그렇죠? 근데 만약에 누군가가 이 이미지는 이런 벡터로 나타내는 게 더 좋아. 그러니까 그게 뭘 기준에서인지 모르지만 그렇게 해서 누군가가 우리가 갖고 있는 이미지들에 대해서 어떤 완전히 새로운 어떤 벡터들을 주는 거예요. 할당을 해준 거예요. 그러면 그게 이제 뭐냐, 그거를 가지고, 그러니까 예를 들면 우리가 그런 픽셀별로 이렇게 나타내는 거를 우리가 뉴런넷으로 아무리 잘 만들어서 해봤더니 뭔가 뭐 무슨 머신러닝 알고리즘 할아버지를 갖다 줘도 이게 학습 데이터가 80%밖에 안 나와요. 예를 들면. 근데 이제 누군가가 갖다 준 이런 이제 새로운 벡터 레프레젠테이션이 있어서 이거를 가지고 뭔가 이제 우리 태스크를 해봤더니 갑자기 레이어 뭐 한두 개밖에 안 썼는데 뭐 성능이 95%가 나온다. 그러면 이게 어떻게 보면 우리 태스크를 기준으로는 뭔가 이 데이터를 보다 잘 표현한 벡터들이 되겠죠. 그럼 이거를 어떻게 만드느냐? 이거를 약간 좀 초벌구이처럼 다른 뉴럴넷을 이제 돌려가지고 이 벡터 레프레젠테이션을 좀 배우는 방식들이 좀 있거든요. 그래서 결국은 이 어떤 데이터를 벡터로 나타낸다. 그리고 그 벡터로 나타내는 것을 배우는 어떤 그 태스크를 레프레젠테이션을. 그러니까 레프레젠테이션 이꼴 그냥 멀티디멘sional 벡터라고 생각하면 되겠네요.
감사합니다.
그 팀플 제한이 3명이다.
네.
그걸 3명만 더 4명으로 지금 계속 진행하고 있어.
아, 그래요?
3명으로 지금 아예 확정을 내버리셔서.
네. 그래요. 그러면은 그거는 뭐 하드한 컨스트레인트는 아니되 하여튼 근데 뭐 사실 4명이 되면 이제 뭐 프리라이드가 좀 더 있을 수 있는 확률이 높아지잖아요. 그러니까 누군가 좀 일을 안 하고 그렇게 될 수 있는 확률이 더 높아지니까 그걸 제한을 좀 하는 거기도 하고 또 여럿이 모여도 또 이게 일이 잘 될 수도 있지만 또 효율이 안 나올 수도 있고 그렇긴 한데 어쨌든 그래서 조금 더 다른 친구들보다 뭐
네.
3분의 4배만큼의 더 기준까지는 아니더라도
1.33배에서 결과물을
네, 그거에 뭐 루트 정도
네, 기준이 이게 n이
네.
너무 낮아서
네.
이제 확 올라가네요. 1.33배.
네.
네, 5명이었으면 1.2배만 이렇게 했을 텐데.
아 그런가? 5명이 3분의 5니까 1.66인가요? 네. 네. 하여튼 뭐 네, 그래서 뭐 완전히 그거를 내가 이제 하드하게 그거를 금지하진 않지만 네, 그래도 뭐 그걸 감안해갖고 좀 더 많은 일을 조금 네, 하는 거를 네, 그렇게 한다라고 생각하면 될 것 같아요.
그냥 3명. 갑자기 네, 알겠습니다.
네.
이거 수업 질문은 아니고요.
네.
그 제가 정보보호라는 과목에서 이제
정보보호?
캡차, 네,
네.
캡차가 요새 뭐 CNN이나 뭐 이렇게 다른 막 발전된 그런 알고 그러니까 그런 거 하여튼에 의해서 잘 뚫린다고 해서 그 잘 안 뚫리는 캡차를 생각을 해보자 하고
네.
하다가 이런 공간 보완 효과라는 거를
음.
찾았거든요. 근데 이게 저희 생각에는 얘가
네, 제목이 뭐죠 이게? 이런 논문 제목이?
논문이라기보다 그냥 구글에 이제 스페이스 컴플리먼트 이펙트라고 공간 보완 효과라고 치면
스페이스
컴플리먼트
컴플리멘트 이펙트.
나오더라고요. 근데 그냥 저희들 생각으로는 얘가 이제 학습을 할 때 이 이미지를 갖고 학습을 하면은 이 뒤에 있는 뭐 R이라는 이 알파벳을 이제 배우려고 하는 게 아니라 이 무슨 뭐 캐릭터 같은 거 이거 덮어져 있는 거 그거에 주목을 해서 자꾸 여기에 맞춰서 이제 그 필터가 트레이닝 돼가지고
네.
그래서 이제 인식이 안 될 좀 어려울 거다라는
네.
추측을 하고 있는데 이게 가능성이 있는 추측인지 맞는지 그걸 저희가 모르겠어요. 어떻게 생각하시죠?
그러니까 이걸로 실제로 뭔가 프로젝트를 하려고 하는 거예요? 아니면
프로젝트.
네, 일단은 뭔가 좀 관련된 논문을 좀 찾는 게 좀 일반적으로 좋을 것 같고요.
네.
그러니까 뭔가 이 태스크 이런 류의 태스크가 전혀 없었다라 그러면 그것도 어떻게 보면 그렇게 좋은 사인은 좋은 징조는 아니고요.
네.
왜냐하면 사람들이 생각하는 것들이 어떻게 보면 좀 비슷할 수 있고,
네.
근데 이제 구체적으로 들어가면 다 달라요. 근데 이제 뭔가 생각하는 것들은 합리적인 선에 생각할 수 있는 어떤 그런 연구 주제라든가 어떤 새로움에 대한 어떤 그 생각할 수 있는 아이디어라는 게 조금은 이제 비슷할 수 있어서
네.
사실 그 관련 웍들을 좀 찾아보는 게 어떻게 보면 가장 첫 번째 단계로서 좀 중요하게 해야 될 일이고요.
네.
네. 그리고 저런 거는 또 어떤 여기 있는 뭐 저기 학생 중에 그 저기 뭐 네이버에서 최근에 인턴을 했던 학생이 또 이런 웹툰에서 뭘 했냐면 이제 웹툰을 이제 누군가가 스크린 캡처를 해갖고 그 유포를 하면
네.
그 이제 유포를 했을 때 이 범인을 잡도록 네. 그러니까 예를 들면 뭐 네이버 웹툰에서 뭐 월 10,000원씩 2명이 보고 있어요. 근데 이제 뭔가 돌아다닌 이미지가 그거를 잘 봤더니 얘한테 내가 배포한 만화예요. 네. 그러면 범인을 색출할 수가 있는 거잖아요. 그래서 그걸 뭔가 그때 용어를 까먹었어요. 네? 어떻게 알아요? 그거 안 해요? 맞아, 저거. 스테가노그래피인가 뭐 저거여서 저게 이제 뭐냐면 내가 각 유저들마다 똑같은 만화를 내가 전송을 해주는 게 아니라 약간씩 뭔가 핑거프린트 같은 약간 그 뭔가를 주입을 해놓는 거예요. 네. 근데 이제 그게 막 예를 들면 뭐 뒤쪽에 뭐 복사 금지라고 이만큼 뭐 워터마크를 달 수도 없는 거고, 그럼 뭐 만화가 좀 질이 내가 만화 보고 있는데 워터마크가 막 뒤에 있으면 좀 거시기하잖아요. 그래서 사람한테는 최대한 노티서블 하지 않으면서 그런데도 이거를 이제 이걸 했을 때, 근데 중요한 건 이거를 이제 만약에 배포를 한다 그러면 그거를 에스펙트 레이시오로 바꿔요. 예를 들면 그러면 내가 주입한 어떤 그 이미지의 패턴도 바뀔 수가 있잖아요. 뭐 그래서 그렇게 되면 내가 또 그거를 디텍트하기가 어려워질 수 있어요. 그래서 이제 그런 여러 가지, 그러니까 여기서 어떤 식의 변질을 거쳐갖고 배포를 했을 때도 내가 로버스트하게 내가 주입했던 패턴이 뭔지를 끄집어내는 거, 이게 이제 스테가노그래피 뭐 이런 거예요. 그래서 그거랑 좀 관련이 있어 보이는 것 같아요.
이거 되게 좋은 아이디어.
네, 그 텀으로 한번 찾아보면 뭐 이것저것 논문이 좀 있어요. 그리고 요 강의에 그 페이페이리라고 이제 이거 강의하고 있는 사람들의 어드바이저 뭐 스탠포드 그 교수가 또 유명한 사람이 있어요. 그 사람이 쓴 논문, 그 사람이 참여한 논문 중에 하나가 그 스테가노그래피 뭐가 있을 거예요. 최근에 나온.
감사합니다.
CNN이 그 지역적인 부분적인 특성을 추출하는데 성능이 좋잖아요. 그럼 필터를 이렇게 사각형에 고정하지 않고 동적으로 이렇게 저쪽 해가지고 얘 보고 그런 연구가 있나요?
있어요. 네.
그래서 더
그게
멀리 있는 거를 보고서
네. 그게 이제 디포머블 필터 아니면 디포머블 뭔가 컨볼루션이라고 그런 게 있어요. 그게 내가 정확하진 않은데 그거가 이게 하여튼 이 레지넷도 만들고 여기 카이밍 해라는 사람이 그때도 얘기했더니 굉장히 유명한 사람인데 그 사람이 했는지 안 했는지 내가 잘 모르겠고 확실한 건 그 마이크로소프트 리서치 에이시아라고 그 뭐 해 이니셜라이제이션 MSRA 이니셜라이제이션을 했다고 했잖아요. 그 MSRA에서 나왔던 논문 중에 그게 있었어요. 그래서 디포머블 컨볼루션인가 이걸로 검색해보면 될 거고요. 그리고 이제 그게 막 무정형으로 막 그 이제 리셉티브 필드 이만큼 하고 내가 내 필터를 여기 위치를 내가 자유롭게 이런 어떤 가능한 모든 조합 중에서 내가 그 어떤 보고자 하는 픽셀을 선택을 하도록 그렇게 모델한테 얼라우를 하겠다, 허용을 하겠다라 그러면 이게 좀 너무 복잡해질 수 있어서 이 필터 자체를 좀 어느 정도 좀 리즈너블한 선에서 좀 플렉서블하게 만드는 것들이 좀 있어요. 그러니까 그게 어떻게 보냐면 그 스트라이디드 컴브 같이 이렇게 이제 3x3에 딱 인접한 결을 보는 게 아니라 가운데랑 하나 건너뛰어서 요거 그렇게 되면 좀 더 넓은 영역에서를 여전히 똑같은 픽셀 사이즈 혹은 컨볼루션에 인발브 되는 파라미터는 역시 3x3 위아래로 3개 by 3개인데 좀 5x5 리전을 보는 거죠. 네. 그렇게 하기도 하고 뭐 어떤 거는 컴브를 이렇게 뭐 이렇게 세모로 이렇게 해갖고 이쪽에서 뭐 그러니까 비디오 같은 거 할 때도 이게 비디오 같은 경우 내가 이제 그 전 프레임이나 그 전전 프레임에서 내가 왼쪽에서 오른쪽으로 움직이고 있어요. 그러면 이제 왼쪽 파트를 바라볼 때 뭔가 그 나랑 비슷했던 패턴이 있으면 내가 이게 좀 그런 걸 디텍트할 수 있잖아요. 그래서 뭔가 사방향에서 그걸 디텍트하기 위해서 약간은 필터가 이렇게
그런 연구
직각 삼각형 4개로 이렇게 구성되는 막 그런 식의 필터도 쓰고 막 이래요. 그러니까 그거는 우리가 어느 정도 여러 가지로 창의성을 발휘해 볼 수 있는 충분히 그런 여지가 있죠.
그리고 여기 슬라이드에서 마지막 최근 거 있잖아요. 어떤 거지?
네.
그 아이디어를 좀 아무리 이해를 못 하겠어.
어떤 거요?
지문에도 올라왔던 건데.
네, 어떤 거요?
그 막 아이덴티티 그
레지넷?
네.
레지넷이요?
네. 이게 무슨
그러니까 이게 레지넷이 그러니까 이게 약간 이런 거예요. 그러니까 이게 레지넷까지 좀 여기까지 좀 설명했어야 되는데 진도가 들어가가지고
많이 다 모르는 것 같아요.
이게 이제 레지넷의 기본 아이디어는 이게 그러니까 완벽한 설명은 아니에요. 그러니까 여기서도 뭐 그냥 어떤 적절한 가설이고 그거를 뭐 완벽하게 증명을 한 건 아니고 그냥 뭐 이런 가설 하에 이렇게 해봤더니 잘 되더라 약간 이런 건데 이제 뭔가 이런 풀리 커넥티드 레이어가 있을 때 예를 들면 우리가 하고자 하는 거는 우리가 지금 우리 태스크가 딱 20레이어까지 필요한데 예를 들면 21레이어까지를 한 레이어를 더 써서 뭔가 뉴런넷을 구성을 했으면 사실 20레이어로 나타낼 수 있는 건 21레이어로 완벽하게 나타낼 수가 있겠죠. 원칙적으로. 왜 어떻게 할 수 있냐면 21번째 레이어를 우리가 그냥 아이덴티티 매핑으로 두는 거예요. 근데 이제 중요한 건 그렇게 레이어를 하나를 더 구성을 하면 이제 학습할 때는 보면 어쨌건 다 랜덤 비주얼라이제이션이 되는 상태에서 어쨌건 그 20레이어 이전 거는 어떻게 보면 그 그레디언트를 거기 20번째 레이어에서 로스가 바로 걸리면 어떤 아주 뭔가 클린한 노이즈가 없는 내가 그레디언트를 받아서 그거 가지고 학습을 하는데 근데 한 레이어가 더 있다? 혹은 뒤에 뭔가 잔뜩 더 있다라고 하면 이게 그 구글넷에서 그 브랜칭을 만드는 어떤 아이디어랑도 비슷한데 이 뒤쪽에 레이어를 잔뜩 붙이면 일반적으로 학습이 어려워지는 이유는 이 뒤쪽에서의 파라미터들이 일단 다 랜덤 이니셜라이제이션으로부터 시작이 되잖아요. 그러니까 그레디언트는 저 뒤쪽에서 원천은 저 뒤쪽에서 발생이 되는데 이 백프랍이 될 때는 우리의 이쪽 파라미터가 곱해지고 이렇게 넘어오고 막 그러잖아요. 그렇게 되면은 여기에 있는 정보들이 어떻게 다 랜덤 이니셜라이제이션 처음에는 이게 전혀 믿을 만한 정보가 아닌데 그런 쓰레기 값들로 뭔가 곱해진 어떤 그레디언트가 처음에 나한테 오는 거잖아요. 그렇기 때문에 이게 그러니까 학습이 일반적으로 더 어려워지는 거예요. 저쪽에서 건너온 그리고 건너온 부분이 그래도 잘 믿음직한 거면 나한테 그 믿음직한 정보가 건너올 텐데 여기가 엉망인데 뭐 원래 처음 정보는 믿음직했어도 이 엉망인 곳을 지나면 당연히 엉망이 되겠죠. 그래서 이제 학습이 뭔가 안 되는 게 아닐까 뭐 이렇게 생각이 되는 거고 이제 두 번째로는 좀 이게 있어요. 그러니까 어쨌건 그 아이덴티티 매핑을 구하려면 이게 그러니까 여기 그거랑 여기가 1, 0, 0 그 다음에 얘는 0, 1 또 0. 그러니까 어떻게 보면 우리의 매트릭스가 여기에 인바이브 되는 파라미터가 총 몇 개가 있냐면 3x3 개의 파라미터가 있어요. 그러니까 이건 비록 컨브는 아니지만 그냥 개념적으로 생각한다면 3x3의 총 9개의 파라미터 중에서 딱 더도덜도 말고 딱 정확한 그 3개는 1이 돼야 되고 나머지의 6개는 0이 돼야지 되는 거예요. 그러니까 딱 그 값이 딱 피팅이 되어야만 이게 그 아이덴티티 매핑이 되는 거죠. 근데 이거를 이렇게 하면 뉴런의 입장에서는 뭔가 사실 막 연결이 얽히설키 되는데 누가 1이어야 될지 누가 0이어야 될지 이거 좀 약간 골아프다는 거죠. 그러니까 이렇게 뭔가 서로 다른 이런 값들을 학습을 잘 해내는 게 일반적으로 좀 어려울 수 있어서 이걸 이제 레지넷으로 구성을 하게 되면 어쨌건 이 인풋이 이쪽에 더해지기 때문에 여기서 학습되어야 되는 옵티멀한 그 아이덴티티 매핑을 우리가 만약에 고려를 한다면 그때 필요한 거는 그냥 누구든 상관없이 그냥 다 0으로만 만들면 되는 거예요.
누구든 상관없이 다 0으로.
그러면 그냥 0인 아웃풋을 내잖아요.
네.
네, 그러니까. 그리고 그럴 때 어떻게 보면은 약간 이건 시그모이드나 이 탄H 쪽 이야기긴 한데, 그리고 또 약간 이런 거가 있어요. 그러니까 탄H나 시그모이드 같은 경우는요, 이게 어쨌든 여기서 우리가 난리니어 유닛을 쓰잖아요.
네.
근데 탄H나 저기 그 시그모이드를 쓰면, 네, 그러면 아이덴티티 매핑을 만드는 게 어려워져요. 왜냐하면 여기에 입력이 들어왔어요.
네.
근데 여기서 선형 변환을 한번 거치죠.
네.
그러니까 어떻게 보면 이게 여기 W가 있으면 WX에 탄 H
네.
이거가 I 곱하기 X가 돼야 되는 거예요. 혹은 I가 아니라 이게 X가 나와야 되는 거예요. 그러니까 이게 애초에 불가능할 수 있어요. 그렇잖아요.
이 함수 때문에.
네.
네.
그러니까 탄 H라는 어떤 아까 얘기했던 뭐 스쿼싱하는 뭐 그런 좀 막 이상한 그래프를 적용을 해서 뭔가 이게 좀 네. 그래서 이게 애초에 탄 H나 이거를 쓰면 아예 아이덴티티 매핑 자체를 그러니까 나타낼 수가 없고요.
네.
예를 들면 그렇게 되면 이게 레이어를 하나 더 쌓았으면 싫든 좋든 이 값들을 내가 뭔가로 변환을 할 수밖에 없다는 거예요. 그러니까 아이덴티티 매핑을 나타낼 수가 없어요. 네. 그러니까 20레이어의 네트워크를 21의 레이어로 가지는 네트워크로 표현할 수가 없어져요.
그렇게 되네요.
그렇게 되죠. 그죠?
네.
그러니까 이게 완전히 다른 모델, 그러니까 하나가 다른 하나를 완벽하게 포함하는 게 아니기 때문에 그런 데서도 이슈가 생길 수 있고. 근데 이제 레지넷 이 리지듀얼 커넥션을 만들면 그러면 그 모든 문제가 깔끔하게 좀 해결이 되죠. 왜냐하면 그냥 심플리 여기만 0으로 만들면 되니까.
그렇죠. 네, 여기를 0으로 만든다는 게 무슨
어떤 의미냐면 그러면 이제 인풋이 뭐가 들어왔던 여기 액티베이션이 0이 되잖아요. 그러니까
네.
이쪽이 더해지면 이쪽이 이제 디지털
그대로
커넥션.
나오는구나.
네.
그 의도.
네.
이해했어.
네.
감사합니다.